Today I will be presenting a work that has been done together with Markus Schmidt, and it regards the extracting complexity of quantum dynamics using machine learning. So in this talk, I will try to put forward a new measure for the local complexity of quantum states. So we know that quantum states tend to be rather complex, as is traditionally characterized by their entanglement entropy. However, even complex, highly entangled states sometimes allow for simple, effective local descriptions, let's say in terms of some emergent hydrodynamics description, or in terms of statistical ensembles. And we try to use unsupervised machine learning to detect such effective, simple local descriptions. So we will characterize this local complexity in the following rather primitive way. We'll simply ask how many parameters we need to reproduce all local observables. And then this approach, using this approach, we will try to, for example, detect different stages of non-equilibrium dynamics, kind of detect whether the Hamiltonian governing the evolution is thermalizing or not, or even to learn the Hamiltonian given that we have access to the local measurements only. And since this approach is essentially totally based on local observables, ideally we could get those from some quantum simulators and then use this approach to analyze the results and even characterize the simulators themselves, since that, as it will turn out, it can even be used to detect some persistent noise that's polluting the measurements. Okay, so somehow to illustrate what I just said in words with an example, let's consider the following situation. So suppose we would initialize the system in a simple product state, it's translation invariant, and thus parameterized with only two parameters at two angles. That's clearly a very simple state. But then if we ran a time evolution with some entangling gates or Hamiltonian, its complexity would grow. However, if we had access only to some local measurements in this state, at some point, these local measurements will no longer be able to detect the full complexity of this state, and will instead become blind to anything else but the conservation laws. So, and we'll be able to essentially describe those measurements by some emergent hydrodynamic description, which relies on the presence of this already mentioned conservation laws. So in some sense, this local complexity will saturate and then reduce down to all the way down to the steady state, which can most usually be described by simple, using some simple statistical description, because as we've learned, for this local subsystem of interest, the rest of the system actually works as a bath, and then for some ergodic system, our local observables are simply given by some Gibbs ensemble. If this time evolution was instead done with an integrable system or system with additional conservation laws, then this steady state description is actually in terms of generalized Gibbs ensemble with additional Lagrange multipliers for these additional conservation laws. And now what we did, so we tried to use neural networks in some sense to compress the information that is contained in local observables and try to extract the physics that I've just explained. And so to do this compression, we used autoencoders which are the neural network architecture shown here, which are outside of physics, literally used for the compression of data. So what they do is that they take some data, and then they try to reproduce it as an output in the output by going through a bottleneck, which hopefully has a smaller dimension. So, and of course, such a reconstruction by going through a narrow bottleneck is possible whenever the data is compressible. So, in our case, each data element will consist of expectation values of local operators. So, say Pauli strings with support up to 3 or 4. So kind of these points here on this schematic representation would be measurements of these different operators, string operators up to support, let's say 3 or 4. And that would be one data element. But to set the network, so we need to train it, so we need several of such sets of measurements of these operators. And these all then contain our full data. And of course, what we are somehow trying to see is whether this input vector here of NO different measurements, whether its dimensionality can be reduced from NO to something smaller that represents its actual intrinsic dimension. And the way we set the network is by essentially comparing here the output data with the input one and trying to kind of match them as good as possible. So trying to minimize the difference between them. And then what you do is, so in the first we train the network to set it, and then we test it on some unseen data sets or unseen measurements of local operators and see how well it performs. And then kind of this test error that I'll be plotting again and again in the future slides is simply kind of this difference between the reconstructed and the input measurements. Okay, and now let's kind of start in the simplest regime, and that is here in the regime of steady states, by trying to use these autoencoders and see whether they can at least, if they can detect that, for example, our measurements are coming or are done with respect to some thermal Gibbs or some generalized Gibbs ensemble parameterized with a given number of Lagrange parameters or kind of these generalized temperatures. All right, so to do so, we will use the integrable transverse field using Hamiltonian, which, as I said, is integrable and actually has a set of additional microscopically many conservation laws. And I mean, we could have really done kind of this quench protocol for different initial states, but we'll instead like first try to benchmark our approach by showing to it cleaner synthetic data coming from kind of synthetic Gibbs or generalized Gibbs ensembles with a fixed number of NC Lagrange multipliers, which are then just drawn from some interval. And of course, what we would like to see is that for a successful reconstruction of the input measurements, we need at least NC, so the number of Lagrange multipliers, neurons here in the bottleneck. All right, so what I'm showing here is kind of this test error, which compares the reconstructed expectation value with respect to the initial one as a function of a number of neurons in the bottleneck. And somehow, as we should, we see that this test error drops when here in the bottleneck, we have at least NC neurons. So it drops at 1 for a Gibbs ensemble, 2 at 2 or 3 at the generalized Gibbs ensemble with 2 or 3 conservation loss taking part in it. So good. So what we've done so far is that we've confirmed that this autoencoder is able to detect the effective dimensionality of our data. Now we can go kind of a step forward and try to understand what did it learn. And it's simplest to start thinking about this, looking at the simplest case of Gibbs ensembles, and try to ask whether here in the like when we know that we need just a single neuron in the bottleneck, and then to ask what is the value here on this neuron for different data elements coming from measurements done at different temperatures. And somehow, as we should, we get that this value here on this neuron is it's an invertible function of energy. So the neural network didn't learn exactly the temperature or the energy density corresponding to this measurement set, but it learned something that is, so that it is a projective function of these two. So somehow, so we see that these values here in the latent space are, for different energy densities of our initial data, dependent in the way shown here in this graph. Good. And now, again, another way to essentially see the same thing is then maybe to allow for 2 neurons in the bottleneck and see where is this, an O-dimensional input vector mapped to in this 2-dimensional space. And then each of these data elements at different temperatures is then mapped into one point in this 2-dimensional space, like this one. And we see that when we show it data elements or these measurements done at different temperatures, these are mapped to essentially a 1-dimensional manifold in the here in this latent space, which is organized with respect to the temperatures. So if we take a few different temperatures, those would actually correspond to a few points here on this manifold. And the important thing to notice is that the way these data elements are organized here in the latent space is really with respect to their energy density, which is shown here by simply coloring these different points with their corresponding energy density. So once again, each of those points would be one set of measurements performed at a fixed temperature. And then different points simply correspond to different such sets at different temperatures. And the important thing is that these are in the latent space, they lie on a 1-dimensional manifold. Okay, and now, so this fact can be actually used to even reconstruct the Hamiltonian from measurements. So suppose that these measurements came from some condensed matter experiment or from some quantum simulator that you wouldn't know the Hamiltonian of precisely. And then you could kind of use the approach that I'll explain now to reconstruct the Hamiltonian. So what one kind of finds out. So as I said, so along this one-dimensional manifold as seen in the latent space, here in this bottleneck space, is organized with respect to the energy density of the input data. But not only energy density, which we pretend we don't know, also the candidate terms from the Hamiltonian will show a large variation, monotonic variation along this manifold. So what we can then do is that we can just check for all of our measured operators which show the largest gradient along this manifold. And of course, as we'll see, like here for the transverse using Hamiltonian, this would be ZZ and X Pauli matrices. Perhaps we'll also find some contributions that are kind of their commutators or their products. And then to somehow get rid of those and really also obtain the correct prefactors of these candidate terms in the actual Hamiltonian, we must on top also compare how the measured expectation values compare to these fictitious thermal ones coming from our candidate Hamiltonians. And then kind of solving for this, we'll fix also the actual weights of these operators in the Hamiltonian. So let me repeat. We can use these autoencoders, first of all, to detect whether when our different measurements are all thermal, and if this is kind of fulfilled, we can go on and even reconstruct the Hamiltonian, given that we have access to measurements at different temperatures. All right, so that was a tiny detour, but now kind of going back to how the different data is seen in the latent space, we can now look at how, for example, generalized Gibbs ensembles spanned by two conservation laws will appear in this latent space, and we see that that like these two orthogonal directions will be indeed spanned by the two conservation laws that are in our generalized Gibbs ensemble. So, and yeah, we'll see how to kind of use these later on to essentially read which conservation laws in more general settings are important for the description. All right, so we've now kind of benchmarked this our method here on some synthetic data coming from synthetic ensembles. So we could be a bit more realistic if we instead really did some quench protocols with, say, this transverse field using Hamiltonian, starting from a different initial state and then running the time evolution to actually like get to these states, and then, for example, ask which conservation laws actually play an important role in these ensembles. So we'll do just a slight variation on this. So on top, we'll also add some weak coupling to baths described by Limrat operators. So this doesn't modify the situation too much, because from our previous work, we know that when these coupling is infinitesimal or weak, the steady states will still be approximately Gibbs or generalized Gibbs ensembles for the Hamiltonian that's chaotic or integrable. So we've heard in the talk by Isabelle Bouchoul that kind of she hinted a bit at why that's the case, but let me perhaps repeat. So what we find in our previous work is that in the case of a weak dissipation, what happens is that if we initialize the system in some initial state, under such evolution, this system will first of all kind of pre-thermalize to a generalized Gibbs ensemble given by the initial state, while later the system will evolve along the manifold of time-dependent generalized Gibbs ensembles into the steady state one, which is actually determined by the baths themselves. So if we started from a different initial state, we would also kind of terminate in this same point. So what we will do now, we'll actually look at different steady states coming from the dominant evolution under the same Hamiltonian, but with respect to different kind of randomly rotated one or two cycling Lat operators. And it will, of course, this description that I just said in terms of Gibbs or generalized Gibbs ensembles is strictly speaking true only for infinitesimal coupling to baths. But when we have finite coupling, we have on top also some additional corrections. And we'll see that if if these different steady states that we obtain from these different couplings to baths have some common features, so these baths have some common feature, our autoencoder will be able to kind of pick this up here in these corrections. That is relevant, for example, for the case when we would run our quantum simulator, which has some persistent kind of structure noise of some form. We might be able to run the program I'll describe in a minute to detect the structure of the noise that's polluting our simulator. Okay, but one thing at a time. So first of all, now let us look again at this test error as a function of neurons we have in the bottleneck. So what we see that when we have the dominant evolution with respect to a chaotic Hamiltonian, that indeed, this test error drops significantly already when we have a single neuron in the bottleneck, meaning that a single parameter, and that's again temperature, roughly pretty well describes our data. Well, we see though that upon adding one additional neuron, there is some improvement, and this must be somehow due to this correction delta rho. On the other hand, when the evolution is with respect to the integrable Hamiltonian, we clearly need more latent variables, at least 2 or 3, to get kind of a comparably good description as in the chaotic case. So we clearly need more parameters, and that's because the steady state is approximately described now by a generalized Gibbs ensemble, and then some further latent variable for the corrections on top of that. Of course, when we ramp up this coupling to baths to be larger, kind of further 1 or kind of 0.2, we see that we no longer have an emergent or a simple description of our system, and we always need kind of more more latent variables in the bottleneck, even when even this simple case of chaotic Hamiltonians. And similarly, it's also kind of hard to tell what these values here in the bottleneck correspond to. While for the chaotic Hamiltonian, this one neuron is clearly responsible to capture the energy density. This is no longer obvious when we have a strong coupling to bus, so somehow, which is signaling that for this data, there is no simple immersion description. All right, so now let's once again look at how our autoencoder sees the data here in the bottleneck. So for the chaotic Hamiltonian, this data is once again spent, so each of these points corresponds to one set of measurements of all operators for one choice of coupling to bus. And we see that once again, this data is spent along one direction given by the energy density. Now, when we have integrable system, the dominant evolution is with respect to the integrable Hamiltonian. When we need also kind of more neurons in the bottleneck, we see that one dimension is spanned by the Hamiltonian, and then the perpendicular one with some linear combination of Hamiltonian and the next most local parity even conservational. And this already, so one thing to notice also in the previous or here in this plot is that even though we could put, even though we have macroscopically many conservation laws in such an integrable system to describe local observables up to support 4, we only need 2 or 3 of them. And we now can see that the 2 most important ones are the 2 most local parity even conservation laws. So autoencoders give us a way to, first of all, detect how many conservation laws are really important for the description of these integrable models, and to some extent also to detect which conservation laws these are. And this can help us somehow build some truncated effective description of integrable systems. But one interesting question remains, and that is what spans here for the case of chaotic Hamiltonian, this perpendicular direction. And to make this more kind of apparent, we looked at different, so the steady states coming from baths that kind of have some clear structure, namely that they favor antiferromagnetic correlations. So somehow they, let's say, flip a spin on site I up if their neighbor is down, and other possible combinations of such leading to this type of correlations. And then we look at the data set coming from Limblets with kind of different weights of those Limblett operators, dissipators with different weights of these Limblett operators. And what we need to see is that this perpendicular direction is spanned by this noise type, so by the correlations that our path was enhancing. And in this sense, so we could use this approach. So by looking for what spans this perpendicular direction in our actual data coming from some simulators, we could look for what kind of noise is potentially enhanced by our simulator. All right, so we've now kind of pretty in great details covered here the steady states in closed and open systems. And now in the last few minutes, let me consider what I introduced in the beginning, namely using autoencoders to detect this information bottleneck. And we will do so using random unitaries we'll use such that have one conservation law, so mechanization conservation, which means that at long times these data, the steady states will be described by ensembles that has one Lagrange multiplier associated with this conservation. And we will initialize the system, kind of as in the example, in translation invariant product states that are clearly described just with 2 parameters. And then we'll run the evolution with respect to translation invariant random unitaries. So at each time steps, so we have the same this random unitaries in this brick wall pattern. And then we feed into the encoder measurements of operators up to support 3. So at each time, we feed in such measurements obtained with different realizations of random unitaries. So these random unitaries are used to give us a rich ensemble of measurements. And then we do this for each time step, kind of independently. And here are the results. So I'm showing the test error as a function of time and the number of neurons in the bottleneck. So we see that this error is kind of low as soon as I have at least 2 neurons in the bottleneck in the initial state, and that's clearly because my initial states are a 2-parameter family. And then at long times, it's slow when I have at least 1 neuron. That's because the steady state is described by an ensemble parameterized with only 1 Lagrange parameter. While okay, that in between, we can clearly see kind of this growth and eventual decay of the complexity, signaling the onset of effective hydrodynamic description. So we can see that, that these autoencoders can be used to detect this kind of entanglement or information bottleneck. Of course, that's just the first step, and it would be much more ambitious and also nice if they could be also used to detect the effective equations of motion, such as this effective hydrodynamic description that applies at longer times. I should, as you see, I've changed from Hamiltonian to random unitaries description, and that's for a reason, because if we use here a Hamiltonian time evolution, starting from these simple 2-parameter states, even at later times, the autoencoder would be able to map these measurements back to this 2-parameter family. So in the case of Hamiltonian evolution, I should mention that this autoencoder is only able to detect the decay of complexity if we start from some randomly entangled states. And that's why using kind of random unitaries is a suitable way to overcome this problem and see this bottleneck in the full glory. yeah, so I've come all the way to the end. So I show you that autoencoders can be used to detect low dimensional effective representations of potentially highly entangled states. And yeah, we've applied this to closed and open systems, and we've seen that it can be used to detect different stages of non-equilibrium dynamics, to kind of distinguish chaotic from integrable systems, and potentially kind of nail down which ingredients of kind of this microscopically many conservationals in integrable systems are really important for local descriptions. And we could even reconstruct the Hamiltonian from the measurements. And kind of this reconstruction in the open systems was possible for the noise type that when our baths that gave us these steady states all have some common feature. And under the outlook, we are currently with my postdoc Sorunandi, we are currently looking at this approach, for example, to characterize the Fouquet evolution, or to learn the Fouquet Hamiltonians in the regimes, or for protocols where the usual Fouquet expansions do not work. Yeah, and with that, I thank you for your attentions, and I'm happy to take questions.